HypDB accepts as input a group by OLAP query and assumes that the query is used for decision making. In this case, with the simple group by query, our goal is to understand what is the effect of choosing between one of the two airlines on flight delay. As we have discussed before, the answer to these naive group by query suggests that American Airlines performs significantly better than United Airlines. In the meanwhile, HypDB discovers automatically from data all factors and attributes that have a confounding effect and make the query biased for decision making. Intuitively, these factors are distributed differently among the groups that we are comparing with the group by query, hence making the comparison unfair and biased. After computing these factors, HypDB picks the factor that has the highest responsibility for making the query biased and warn the user that further grouping by this additional attribute may radically change the insight obtained by the original query. In this case, as you observed here, HypDB identified origin as the highest responsible attribute for making the query biased. And as we have discussed before, further grouping by origin totally reverses the trend obtained from the original query. The next step is to remove bias from the query. In order to remove the bias, HypDB rewrites the query to control for the confounding effect of confounding attributes. The query shown in this box is the rewritten query associated to the group by query that we started with. Please refer to the paper for more details about this query rewriting. For the moment, note that under certain assumptions, the insight obtained from the answers to this rewritten query are unbiased and support decision making. In this case, the answer to the rewritten query revealed that it is actually United which performs slightly better than American Airlines. Hence, HypDB resolved the Simpson's paradox. Finally, HypDB generates two kinds of explanations for the biased query: fine-grained and coarse-grained. Coarse-grained explanations rank the confounding factor by their responsibility for making the query biased. In this case, as we have discussed, origin has the highest responsibility. As you observed here, more than 50% of the bias is due to origin. But there are other factors such as different flight departure time that we need to account for. Fine-grained explanations drill down into a particular confounding factor and explain how the ground levels of this factor make the query biased. In this case, the top 4 fine-grained explanations for origin indicate that United Airlines frequently flies from airports such as Rochester Airport that has a lot of flight delay, whereas American frequently flies from airport such as McAllen Miller that has fewer delay. Therefore, the original query that we started with is clearly biased toward American Airlines. Now let me briefly explain how HypDB discovers the confounding variables. An algorithmic approach for finding the confounding variables was developed by Judy Pearl, who assumes that we are given a causal diagram over the set of attributes where an edge represents a potential causal effect between attributes. Then a sufficient set of confounding variables for removing bias from queries can be read off the causal diagram, if they are available. HypDB does not assume any causal diagram. Instead, under the hood, HypDB uses a novel method for discovery of a potential set of confounding variables that does not compute the entire causal diagram, but explores only the subset that is relevant to the query at hand. We empirically show that our method is competitive with the state-of-the-art causal diagram discovery algorithms, yet it scales well with large and high-dimensional data, and it's robust to sparse subpopulation. With this, I will jump into the conclusions. OLAP queries can be biased and misleading for decision making. We propose HypDB, the first database system to detect, explain, and resolve bias from OLAP queries. We show with several examples in the paper that HypDB is useful for avoiding statistical anomalies such as Simpson's paradox, avoiding false discoveries, detecting discrimination and reasoning about algorithmic fairness, and finally, detecting errors in data collection. Thank you for listening.